Well, in this video we will see push down automata. In the previous videos we have discussed about finite automaton. So the limitation of finite automaton is that it does not have any memory. So there are certain limitations. For example, we have proved using pumping lemma that the string ai, a raised to I, b raised to I, or some 0 raised to n, 1 raised to n. I mean patterns like this where it needs to keep track of the numbers cannot be done by DFA because it exceeds only things that are possible without any memory. So that is the limitation of DFA or any finite automaton for that matter, whether it is DFA, NFA or epsilon NFA. But in case of push down automata is actually a finite automata with stack. Okay, so if we are speaking very precisely, that is actually an epsilon NFA with stack. That is, it is kind of an NFA because it can have non-determinism, then it can have epsilon moves, and it is backed up by a stack. So precisely push down automata is actually an epsilon NFA with stack. Just like finite automaton, it is very easy to implement push down automaton as well. So we will see examples. We will see one example in this video, and we will dedicate another video just for more examples. So giving you the tuple representation for PDA. A PDA P is actually the tuple Q, where Q was the set of states, sigma, where sigma is the input alphabet, then there is tau. That is the first difference compared to DFA, since it has a stack. Tau is the set of symbols which can be pushed into the stack. That is symbols that can be pushed to stack. That is that, or push down symbols. That is what tau is. Now it has a transition function delta just like that of DFA, slightly different. I'll tell you what exactly is it. But it has a push down function. Now it has Q0, the start state. Similarly, it has Z0, the start symbol, because it always have a bottom mark symbol in the stack. So Z0 is the start symbol which is usually present at the beginning in the stack. So Z0 is the start symbol. Now A or F can be used to represent the final state. So it is 1, 2, 3, 4, 5, 6, 7. It's a 7 tuple. Yeah. Now tau, as I told, is the push down alphabet or the set of symbols that can be pushed down into the stack. It can include symbols from sigma also, or it can have extra symbols. Now delta is a transition function. So the here delta has arguments, a state from Q. Now it can have any symbol from sigma, or it can even be epsilon as I told, because it is almost like an epsilon NFA. So the input can be either taken from sigma or from this epsilon. Now it has the stack alphabet tau. It can have a stack top symbol which is taken from tau, and in the output it can have a state, one or more states, because as it the reason for saying one or more is it can be non-deterministic. So a state from Q and symbols from tau. So because the stack top symbol that is taken from tau. So this is the representation for the transition function delta of a push down automata. It has a symbol. For example, the transition functions are written something like this: P, now some 0, now dollar is equal to Q, then $1, something like this. So if we write this, this means that initial state was P, then when the input 0 is given, when the stack of top contained delta, the new state obtained is Q, and 1 has been inserted or pushed on top of dollar. So this is how we write transitions. Again, this will make more sense when we see an example. And again, before going into the example, let's see one more thing, that is the PDA terminology. That is, when if the stack is like X and if we are pushing Y, we will get the stack as XY, isn't it? So, in case of PDA terminology, we will say that X has been replaced by YX. So this is how we represent this move in the PDA terminology. So that is, this X has been replaced by YX. X is replaced X by YX. This is how we represent it in case of PDA terminology. Or if it is pop operation like Y, X, and if we are popping Y, pop, then you know that it would be simply X, isn't it? So we write it as, in PDA terminology, we write it as replace Y by epsilon. That is, Y has been replaced by epsilon. This is how we denote this in the PDA terminology. I am explaining it in the beginning so that the examples will be easier for you to understand. Okay. Now again, the PDA can accept a string in two ways. First one is acceptance by final state, just like we do in case of DFAs and FAs and all. Once we reach a final state, we can say that the string is accepted. That is one way of acceptance in the final state. The second way of acceptance is acceptance by empty stack. That is, at the end of the input has been completely processed, and if the stack is empty, we don't care about the state we have reached, we will say that the string is accepted. If we are designing PDAs for acceptance by empty stack. So these are the two strategies. In final state acceptance, the stack may not be empty. We can have stack contents, but once we reach the final state, we say that the input is accepted. In case of empty stack acceptance, the stack will definitely be empty. We don't care about the state we have reached. We say that the string is accepted if the stack is empty and the input has completely been processed. So when you design a PDA, you can design PDAs for PDAs which follow either of these two strategies. Okay. So now we will jump into an example so that everything will make sense to you. Okay. So we will do the example. We will do the example which was impossible with DFAs. This is one of the things which a DFA cannot do. Anyway, PDA is much more powerful than a DFA. PDA can do many things. So DFA is known as type 3 formalism. PDA is type 2, and PDA is definitely stronger than DFA because PDA can do many things DFA cannot do. Okay. So again, we have deterministic PDA and non-deterministic PDA, just like deterministic finite automata and non-deterministic finite automata. But here the difference is, in case of finite automata, both DFA and NFA were computationally equivalent, isn't it? But in case of PDA, non-deterministic PDA is much more powerful than deterministic PDA. And we can't, because of this thing, we can't always convert non-deterministic PDA into deterministic PDA. Because deterministic PDAs can do much more things and they are stronger than deterministic PDAs. We will see examples for all these things, that is for empty stack acceptance, for final state acceptance, for deterministic PDA, non-deterministic PDA, everything in the next video when you work out on examples. But in this video we will see an example and we will concentrate on defining the terminologies and notations here. So I'll design PDA for A raised to n, B raised to n, which was impossible with finite automaton. So we will design PDA for this. So as I told, please to remember that PDA has a stack which can keep track of symbols, and you can insert any symbol into the stack. Okay, that symbols will be added to 2, that's it. So A raised to n, B raised to n. So the idea here I am using to solve this is, whenever I see A, I'll push that into the stack. All the A's that I encounter will be pushed to stack. and whenever a B comes, I'll pop an A. So at the end of the input is empty, that string will be accepted. That's it. So initially I'm at state Q0. So when I am at Q0 and my stack contains the stack bottom in marker, usually we use dollar to mark the beginning of the stack or bottom of the stack, and this is Z0 now. So dollar is my Z0. So if I see when I am at this stage, if I see A on the input and dollar in the stack, if I see A in the input and here A and N is greater than or equal to 1. Okay. N is greater than or equal to 1 here. So when I see A, if I see A and top of stack is dollar, I'll simply push A to the stack. That is, I'll replace dollar by A dollar. This is what I mean by this representation. See, this notation means that if you see A in the input, if you see dollar in the top of stack, you will push A to the stack. That is, A will stack top will be replaced by A dollar now. That is, A has been pushed. Okay, so that is what happens when the first A comes. So that has been pushed. When the second, for example, if the input is AABB, when the second A comes, the stack top is A, isn't it? So that also should be coded. So when the input symbol is A and if the stack top is also an A, I will again push the A. That is, I will replace this A by AA. So the new A has already also been pushed. Now if I see a B, what I am doing is I will pop the corresponding A of the stack, isn't it? So if I am seeing a B and if the stack top is A, I will pop the B of the stack. That is, I will replace B by epsilon. That is, I will not push this B. I will pop the B of the stack. Okay, pop the A of the stack. Sorry. So I'll pop the A of this stack. So I'll represent it by giving epsilon. As I told, the stack top A has been replaced by epsilon. So this A has been replaced by epsilon. Okay. Now when and I am changing to a new state to mean that I am in the popping state now. So if I see more B's and if the stack top is A, I will be popping all such A's out. So when this B comes, this A will also be popped. Okay, now I have reached the end of input. That is, input is empty now and the stack top is dollar now. When the input is empty and the stack top is dollar, I can take the dollar off if I want. That is, I can pop the dollar off also if I need, and I can go to the final state QF. So this is the push down automata for A raised to n, B raised to n. That is, as I explained, the logic is all the A's will be pushed to stack. So when first A comes, it will be pushed to stack. When second A comes, that will be pushed to stack. And the first B comes, this A will be popped off the stack. And the second B comes, this A will be popped off the stack. So when you reach the end of the input, the stack will contain simply dollar. So you may pop the dollar off of the stack if you need, or you can leave it unchanged. Now you will reach the final state. So this is the push down automaton that accepts strings of the form A raised to n, B raised to n. So this is how we write it. Okay, so in this example I have shown the final state acceptance. You can also make it as empty stack acceptance. That is, if you don't have to go to a final state, you can go to another state Q2. But again, if you are designing this for final empty stack acceptance, this indicate that the string has been accepted, because at the end the stack is empty, because you are even popping this dollar of the stack, isn't it? So you can say that this is empty stack acceptance. Empty stack acceptance means at the end of processing the string, the stack should be empty. So here stack is also empty. So you can, just by making slight changes to the diagram, you can make it either final state acceptance or empty stack acceptance. Both of them are equivalent also. If you want to write down the transition functions, it's very easy to write. Delta Q0 A is the input symbol, dollar is the stack top symbol. Then in that case you go to Q0 itself, and the stack top is now A dollar. Now the second transition Q0. Now if A is the input symbol, A is the stack top symbol, you stay at Q0 and the stack top contain AA now. First symbol is A, on the top of the stack you have A, below top you have another A. That is what it means. Now delta Q0, if the input is B and the stack top is A, you go to state Q1 and you push the, you pop the symbols of the stack. Now delta of the state is Q1. If you are seeing B and if the stack top is A, you go to Q1 itself, but you pop the stack top symbol. Now if you are at Q1 and if the string has been completely processed and the current symbol in the string is empty, and if you are having dollar on the top of stack, you may go to state Q2 and pop the dollar off of the stack. That is up to you. Okay. So this is how you convert this into transition functions. Again, there is something called instantaneous description for PDAs, which shows what happens when particular input is given to a PDA. So it can be written like this. So for example, if Q is the state and if AW is the input string, and if some alpha was on the top of the stack, you can write it as this. Will take you to, this is the transition or trans style. Now when it will take you to the new state P, A has been consumed, so remaining input is W and the new stack top will be some beta, because the stack top may change. So this is how you represent instantaneous description. This means in one move. If we are putting a star, this means 0 or more moves. Yeah. So we will see instantaneous description when a particular input is given to this PDA. For example, when the input AABB is given, initially PDA is at state Q0. When the input AABB is given, the stack of the top of the stack contain delta in the beginning. So this is what happens in the beginning. So what it gives us, you are at state Q0 itself, but A has been consumed. So the remaining symbols are ABB and the stack top is A dollar now. Okay. Now in the next move, what happens is when Q0 when A is applied on Q0, the stack top is A. So what happens is you are at state Q0 itself. A has been consumed, so the remaining string is BB and A has been pushed to stack. So this stack top is A dollar. Okay. Now when Q0 encounters B and on the stack top it is A, what happens is it goes to state Q1 and the B has been consumed. So the input is simply B, and you are popping this O of the stack. So the stack top is A dollar. Now when Q1 sees another B, it states at Q1 itself, this B has been consumed, so this is empty, and this A has been popped off of the stack. Now when Q1 sees epsilon and the top of the stack is dollar, what happens is it goes to the state Q2 and the input is empty now and it is popping, and by this design it is popping the dollar off of the stack. So this is empty. So This is how you write down the instantaneous description. That is what happens when an input is applied. Instantaneous description or ID of a PDA. Okay. So as I told, a PDA can accept strings by two ways. Either by final state. If it is by final state, a language accepted by final state can be written as the language is any, all the strings W in the language will be accepted such that when it is in initial state Q0, when W is applied and when Z0 is the top of the stack, that is usually that indicates the start symbol in the stack. In one or more moves, you will, I am talking about final state acceptance, you will reach the final state. You will reach a state QF, where QF is element of the set of final states. The input string will be empty. When you reach the input will have been completely processed, and the remaining stack top can have simples. It doesn't matter. Okay. Stack top can have simples. Okay. So this will be the state. So here QF is element of the set of accepting states A, and alpha is actually element of tau star. That is, alpha is made up of strings from tau. Okay. So this is how you represent final state acceptance. That is, a language L is accepted by final state when all the strings W is accepted such that when W is given to Q0, the initial state, when the stack top contains Z0, the stack bottom marker, in 0 or moves, you reach a final state QF, where QF is element of A. Input will be completely processed and the stack can have something. Stack is element of tau star. It can be empty also. Okay. So if we are speaking about empty stack acceptance, I am making changes to this equation itself so that you can easily relate to it. So empty stack acceptance can be written as when you are giving W to Q0, when the initial stack symbol is Z0, you may reach some state. It need not be any state from the final state. You reach some state P, and the input has been completely processed and the stack is also empty. So this is how you denote empty stack acceptance. So these are the basic things about a push down automata. It contains a stack, so it can memorize certain things, so it is more powerful compared to finite state automaton. Now it can accept strings using either an empty stack or a final state. It is completely up to you. You can design it in either ways. Anyway, both of them, that is final state acceptance and empty stack acceptance, are computationally equivalent. Nothing add any power to the design compared to the other. Now there are non-deterministic PDA and deterministic PDA. Non-determinism certainly adds some power to PDA. So you can't generally convert a non-deterministic PDA into deterministic PDA. This is known as type 2 automata, where DFAs, NFAs and epsilon NFAs were type 3 automaton. So this is how we represent instantaneous description. So hope this is clear. Thank you.